In this example, we're asked to show that this series is telescoping and then to use that fact to find its sum. So telescoping is a property of the partial sum. So let's write this out. First of all, our series itself is the sum. N starts at 2 to infinity because otherwise we'd be dividing by 0. 1 over n squared minus n. And as it's written, this doesn't look like it's telescoping at all because this is just going to be what? 1 over 4 minus 2 plus 1 over, the next term when it's 3 is going to be 9 minus 3, plus the next term is going to be, when n is 4, it's going to be 16 minus 4, etc., right? And so this doesn't look like it's telescoping at all. These terms are not going to cancel out. This is a half, this is a sixth, this is 1/12. But this term, 1 over n squared minus n, can actually be broken down by partial fraction decomposition. Okay, so this can be written as, let me do this in 2 steps. So this can be written as 1 over n times n minus 1. All right, and then we can try to break this up into a sum of something over n plus some other constant over n minus 1. All right, and you could do this one by guess and by golly, honestly, if you wanted to, or you can do this by the partial fraction decomposition method, which is to multiply both sides of this, n squared, by the common denominator. So I'm looking at both sides as the far left and then all this on the right, n squared minus n times all of this. And what happens? Well, on the left-hand side, the denominators just cancel, and so we're left with 1. On the right-hand side, some of the denominator cancels, but then the other part, the kind of the opposite denominator, does not cancel, right? And so we end up here with a times n minus 1 plus b times n. And this equation must be true for all values of n. And it actually must even be true for the values of n which make this fraction undefined. Okay? So we can plug in what we call convenient values for n. So when n is 0, the left-hand side is still 1. There's no n's here. It's always going to be 1. This side becomes minus a times negative 1, plus 0. And so this tells us that a is equal to negative 1. All right? When n is equal to 1, something very similar but slightly different happens. We still have a 1 over here. Now the a is zeroed out, and we get plus just b, and so this tells us b is equal to 1. All right? And all this work then tells us that the summand, the thing inside, the term inside of our sum, 1 over n squared minus n, is the same as what? Negative 1 over n plus 1 over n minus 1. All right? Or this could be rewritten as 1 over n minus 1 minus 1 over n. All right, well, let's, maybe even better, if we want this to match the notes that we've studied, we want this to be some term minus the previous one, right? So we can factor the minus sign out here and write this as 1 over n minus 1 over n minus 1. All right, and then we have a result in the notes, and in the notes this result says this. It says the sum of, if we have, say, n goes from, let's call this j to k, and if the entries in here are a sub n minus a sub n minus 1. This is called a telescoping series, and so in the notes it's worked out why exactly this happens, but this ends being then a sub k minus a sub j minus 1. All right, and so for what we're concerned with here, if we write down our partial sums, we draw a little divider here. Remember, we have the sum, n's going from 2 to infinity, 1 over n squared minus n. This is equivalent now to negative, that minus can come out. Well, maybe not yet, but it can, we'll write it inside here. It's negative 1 over n minus 1 over n minus 1. Okay, and if we regard, so we're going to look at the partial sums here now. So s sub k is going to be the sum. N goes from 2 to k of this negative 1 over n minus 1 over n minus 1. And at this point, this is a finite sum, so the minus can come out. So now we have a minus sign, and then we have our telescoping sum. N goes from 2 to k, 1 over n minus 1 over n minus 1. All right, and according to this formula, what's this going to give us? It's going to give us minus 1 over k minus 1 over 2 minus 1. All right, and then this minus can get distributed back in, and look what we have. We end up with 1. This is 1, negative 1, but we distribute the minus, minus 1 over k. So the partial sum for this series, which didn't necessarily look like it was going to be telescoping to begin with, the partial sum is absolutely telescoping, and it gives us this very nice closed formula. So our partial sum sequence, our sequence of partial sums, S sub k, is equal to the sequence 1 over 1 minus 1 over k. All right? And remember, the sum, if a sum of an infinite series exists, then it has to be equal to the sum of the sequence of partial sums, right? It has to be equal to the limit, of the sequence of the partial sums. And so the sum of our series is going to be, so this is our sum, n goes from 2 to infinity, 1 over n squared minus n. This is equal to the limit, k approaches infinity, of s sub k, which is the limit. K approaches infinity, 1 minus 1 over k. This distributes, 1 minus the limit, k approaches infinity, 1 over k. As k gets very large in this term, then 1 over k gets very small, and this limit just equals 1. And so, with all this work, what we've shown is that the sum, n goes from 2 to infinity, of 1 over n squared minus n is just equal to 1. All right? Convergent series adds up to 1.